Hi, welcome. Today we're going to talk about residue processing. In our last video, we already found out that besides cracking the vacuum gas oil, hydrocracking the vacuum gas oils, you can also hydrocrack the residue. It's a process known as residue hydroprocessing. If you are looking through patterns, you can find out about it. I'll show you all the patterns I'll be going through in the description below. Now, the most simple way we can do our residue hydrocracking is to follow the similar design as our vacuum gas oil hydrocracker. So, the only difference between residue, vacuum residue, versus vacuum gas oil is a vacuum distillate or vacuum gas oils. The difference is that this stuff is really dirty. What do I mean by that? It has the most sulfur, the most nitrogen, and the most metals, and the most coke forming tendency. So it has the potential to form lots of coke. That's why it's called dirty. And let's say you do have a similar setup as the standard hydrocracker. So let's say you have vacuum residue. Okay. And maybe you want to filter some of the dirt out, because all the dirt in the oil will be concentrated in this fraction. This is the bottom of the bottom, so all the dirt and everything will be concentrated there. So maybe you want to filter out some of the dirt. Alright. And then you add some hydrogen. Okay. Maybe you mix it through a heater. And just the same as the hydrocracking process, you go through a guard reactor. This is where the hydrotreating will occur. So you'll get rid of the impurities and anything else that could poison and interfere with the cracking process. So it comes out and it goes into the second reactor. Of course, in between the stages, you can actually just separate out the sulfur, the H2S, the NH3. Okay, you can separate it out halfway, or you can choose to put it into the second reactor. It's a hydrocracking reactor or hydroprocessing in this case. I mean, the process is quite similar to hydrocracking, okay? So there's nothing too much different. Don't worry too much about the terms over there. Just that hydroprocessing is more often used for residue. If you want even more conversion, you can put it in a third reactor. Or, for the other reason you want to have a third reactor is to split the second reactor in half. Now, what do I mean by that? Now, let's say you have your hydrogen and residue mixture, and you react it in a tube-shaped reactor. As you react the hydrogen with the residue, it gets hotter and hotter. So by the time it gets to the end of the tube, it gets really hot. So you can imagine in a very long tube, sometimes that tube will overheat, and in this case, overheating means exploding. Right? High temperatures, high pressure, and a lot of hydrogen. That could get really ugly really quickly. So what can you do? You cut this tube in half, and then you have the same H2 with the residue. Halfway through, you cool or quench, or you can put in some fresh H2, fresh hydrogen. Now what the fresh hydrogen does is to dilute the mixture and to cool it down. So let's say you have a cold quench of hydrogen. You have extra hydrogen that being added. The whole temperature of this mixture will start to dip, so that you can start to react more of it. So at the end, you have your converted final product. Okay? So that is why you probably have 3 reactors. Now the last part, you can separate out the various products. And of course, you fractionate it. You separate out the hydrogen from the nasty gases and from the oil. And pretty much you have the fixed bed residue hydrocracker or residue hydroprocessing. Now one of the processes that uses this kind of setup is called the ExxonMobil resid fining process. Okay, so again you have vacuum residue feed. You mix it with a filter, and this is a heater, right? A furnace. What they do is that they pump the hydrogen gas into the heater right away. Instead of heating the oil directly, you heat the hydrogen. And why is that so? If you start heating the oil prematurely, then the thing can start to crack. But if you heat the hydrogen doesn't crack. And if cracking happens in the presence of hydrogen, the coke forming tendency is a lot less. So in effect, the heat only comes with the hydrogen. Okay? So since the heat only comes with the presence of hydrogen, you minimize the coke forming tendencies. Okay, so first we go through our guard reactor. Now this is our filter, yeah? So guard reactor, probably using something like silica alumina on cobalt molybdenum. That's the catalyst. And after that, it goes through the second reactor. These are all fixed bits. And when it comes out hot, and it comes out in very high pressure. This is a lot of energy you can use for the separations. So to make use of this energy, instead of just using cooling water to cool it down, we use the energy to separate it out first. Because when you use this energy to separate things out, your overall energy consumption is less. So this high pressure can do something. This high pressure can be anywhere from 138 to 207 bar. And this temperature can be as high, perhaps as high as 400 plus degrees C. So, what can we do? This is a mixture of hydrogen sulfide, ammonia, other nasty gases, and oil. So under high pressure, all these will be probably in liquid form, right? All these will be liquid or dissolved. So what you want to do is to separate all these from the oil. So the first thing to do is to depressurize. You depressurize in a high temperature separator. Alright? So what goes up the top will be hydrogen, H2S, and H3. Hydrogen sulfide, ammonia. And whatever comes out the bottom will be hot oil. So here there will be still some pressure. So you have a low temperature separator. Okay. you have a low temperature separator. Okay, so the heavy oils will go down. I forgot to mention there'll be some of the light hydrocarbons over here. Excuse me. Yeah, the light hydrocarbons will be over here. So these light hydrocarbons can combine with the heavy oil, and you can send it to a fractionator. So again, here in the fractionator, you'll be split into the various products. And all of this stuff here will be quite low sulfur, low nitrogen. But of course, you know that the hydrocracking process actually makes olefins. Sometimes they are not saturated well. So some of the hydrogen sulfide gas can combine with the olefins to form mercaptans. Mercaptans are the sulfur-containing oils. So some of them still happen here, so you might actually have to hydrotreat these compounds again before sending it to the reformer. Or sometimes you want to hydrotreat this to make it into a very ultra low sulfur diesel kind of content. Okay, so this stream here is light hydrocarbon. Whatever comes out the top will be a mixture of hydrogen sulfide, and ammonia. So yet another separator. This time it's called a stripper, where the hydrogen sulfide and ammonia are stripped, either using water or using an amine. So this is the amine water stripper, and this will then be recycled with a compressor, because this will be relatively pure H2, relatively pure hydrogen, put it through the compressor and send it back to the beginning. So that will be the hydrogen recycle. Okay, and that's pretty much it for a fixed bed hydroprocessing process. And you might wonder why you want to use a special stripper for this hydroprocessor rather than, a simple separator. Because the nitrogen and hydrogen content and nitrogen and sulfur content of residue is so much higher that the hydrogen sulfide and ammonia content inside this gas may be too high to be desirable. That can form impurities, and it can form a lot of problems. So to get rid of it, you probably want to use something like this amine stripper to get rid of it as much as you can, so that whatever you cycle back will be relatively pure. It won't have corrosion problems or any other kind of problems. Okay, now this is just one of the kinds of hydroprocessor. The other one I want to talk about is a more common kind. It's called the Ebullated bed. Now, what happens in this case? Let's say you have all these hydrocracking reactors and the hydrotreating reactor, of course. But the thing is, because you need to crank up your temperatures in these reactors to be really high, more than 400 degrees sometimes. Okay, and what that can form is that what can happen is that a lot of coke can form in a fixed bed reactor. This is due primarily to the reason of there being hotspots. Now, what do I mean by hotspots? Okay, let's go back to an example, a very common example of cooking steak. So let's say you have a piece of steak here, And let's say you have some fire, okay, and you want it to be cooked, let's say rare. So you turn up the heat really a lot, so that the outside of the stick is seared. However, the center is not really well cooked, but the outside is burnt. So what happens is that, while the whole stick itself is not really cooked well, there's a part of the stick that actually experiences a lot more heat than the rest of the stick. Thereby, it forms a burnt residue and forms carbon. So it kind of like has the carbon or coke kind of a thing at the bottom. Now the same thing can happen in a fixed bed reactor. While some of the oils are not as well converted, there may be hot spots. There may be hot spots inside these reactors, and a lot of coke can form. Now what can you do to prevent these hot spots? Well, if you could mix your stick up rapidly, if your stick was in a liquid form, I suppose you could actually prevent the burning from occurring so that the cooking is more even. I mean, the other way again is you can look at scrambled eggs. So the scrambled eggs tend to form a cooked layer at the bottom. If you don't mix your scrambled eggs well enough with, let's say, a ladle or something like that, the bottom could overcook and the top would be undercooked. So, to prevent the burning, you do a bit of mixing. Now that's exactly what they try, what the objective is for the Ebullated Bed Reactor. Okay? The Ebullated Bed Hydroprocessor does basically this. So with hydrogen and oil, okay, you have hydrogen and oil, and that inside this Ebullated Bed Reactor, you have, instead of a fixed bed, the bed is actually circulating inside. So this has to flow at a very high velocity, high flow rate, to cause the catalyst particles and the hydrogen and oil to be mixing around in the reactor rapidly. So actually what they sometimes do is, instead of taking all the effluent out, they pump back of it using a recycle pump. Let me go and draw this here. Okay, just pretend there's a pump here, okay? This black box here, just pretend it is a pump. Okay? So they pump back some of the effluent back into the reactor to increase the flow rate, so that the reactor can keep circulating and circulating. This will prevent the hot spots from occurring, and this will reduce coke formation. You can read more of this in the patent US 2987465A. It's one of the early patents talking about the concept of the Ebullated Bed Reactor. Now, the good thing about an Ebullated Bed Reactor is that you can do online catalyst replacement. Okay. Okay. So not only is the bed not fixed, okay, so there's effluent here, there's hydrogen and oil mixture. So just imagine the recycle system is already inside like this. Well, what you can do is this. You can put some of the fresh hydrocracking catalyst in, and you can take some of the old catalyst, or they call it the equilibrium catalyst. You can take some of it out. This is just the idea of online replacement, so that you don't have to shut down the entire reactor here to keep your unit running. Because even though there's less coke, some of the coke and some of the metals will still deposit on this. And given that it's a very dirty kind of feed because it's vacuum residue. Okay, it's vacuum residue feed. There's a lot of metal, a lot of impurities that will just deposit on this. So similar to the FCC unit, a fluidized catalytic cracker, you can refuel it online. Okay, so this idea was discussed in the patent US 361 7524A, which talks about the online catalyst replacement of the excuse me, Ebullated Bed Reactor. And what does an actual Ebullated Bed Reactor look like? I mean, what does the flow scheme look like with the recycle pump and everything? So let's say you have a reactor like this. Okay, so this is just a separate compartment, all right? This is a separate compartment, and let's say you have all your packed beds over here, or your ebullated beds, which is a bubbling bed. It's a fancy word for a bubbling bed. Okay, so feed oil and hydrogen, which is the vacuum residue and hydrogen, is pumped through the bottom. And this whole thing here is a recycle pump. So the Ebullated Bed Reactor, I mean, it kind of does this, alright? So the catalyst will be circulating within this region. However, in this region, only the hydrogen and oil, and the oils will be circulating. So only hydrogen and oil will be in this layer. Here will be catalyst, hydrogen and oil. So some of the hydrogen and oil can get pumped back down the bottom, similar to this, except here it's inside the reactor. It get pumped back down to the bottom so that the flow over here can increase, so that the bubbling, the ebullition, the Ebullated Bed Reactor can continue. So the effluent, I mean the products of this reactor, can be extracted through here. And of course you can put in catalyst addition here. And you can take out the catalyst from here. Okay. So basically, what you can have, the kind of setup you can have, is instead of having these 3 fixed bed reactors, you can replace all these with Ebullated Bed Reactors. And that will give you a different kind of process. This is called LC finding. And what's the typical temperature, pressure, and linear hourly space velocity? Liquid hourly space velocity. So for this, the liquid hourly space velocity is 0.2 to 0.5. It stays there even longer than a hydrocracking reactor. Hydrocracking can be about 0.65. So this stays a lot longer in the reactor for obvious reasons, because it needs more time to react. Pressure 138 to 207 bar. Temperature 425 to 455 degrees C. Okay? Catalyst, as explained before, silica alumina with cobalt molybdenum. Okay? Of course, these aren't the only kinds of reactors. There's also one more kind of reactor they call the HyCon. This is a moving bed reactor, but I'm not going to cover it in this video because it will take really long. You can go read more about it yourself. It's just a slight modification from what you've already seen. I mean, the process is more or less the same. So HyCon's by Shell, and this resid finding is by ExxonMobil. Okay? Thanks for watching, guys. Hope you've enjoyed this video. I'm gonna see you guys next time. Bye.